Hey everyone. So welcome to a new unit, radicals. So in 10C, we dealt with radicals, the concept of a radical. We did changing from something called mixed radicals to entire radicals, as well as simplifying, which was looking at sort of entire radicals to mixed radicals. The purpose of this first lesson is really just it's twofold, really. It's to review all the things we've done in grade 10, okay? Just to make sure we're all on the same page, get that little rust off of our thinking. And then the second portion is to deal with throwing some variables in here as well, okay? And how do we deal with the variables when they're underneath a radical sign, okay? So I'm hoping this first lesson is not too bad on anyone. If some of the things I do today is a little stressful for you, I do want to encourage you to go back then and take a look at the 10C videos on simplifying radicals, okay? I think there's 2 videos around radicals that would be really, really good for you to take a look at, okay? All right, so to start with, we got to just review a little bit of exponent laws. Simplify the following expressions. State any restrictions on the variables. Well, when there's just a base as a variable, that variable can be anything I want, right? So there are actually no restrictions there. When multiplying powers of the same base, I would be adding the exponents. So x cubed times x cubed would give me x to the 6, okay? Here, I have a power of a power. Again, my variable is a base, and I can put anything I want for y, so there are no restrictions here. When I have a power of a power, I multiply the exponents together, so that ends up being y to the 6. Okay. All right, so now this is an outside exponent. This outside exponent applies to each guy inside here. So this is 5 to the 3. 5 to the 3 is 125. This would be x to the 3. And then this would be y to the 4 to the 3. So that's a power of a power. I would multiply the exponents together, okay? So I end up with 125, x to the 3, y to the 12, okay? A common mistake that kids make, just FYI, a common mistake kids make is they get caught into thinking, oh, I have to multiply this by 3, and this is a 1, so I have to multiply it by 3. Nothing I've said there was wrong yet. But then they go to this 5 and they say, oh, okay, so 5 times 3 is 15. That's not 5 times 3, it's 5 to the 3. So just be careful with that, right? 5 to the 3 means 5 times 5 times 5. It's 5 times itself 3 times, okay? You all have an exponent button on your calculator. It should look probably like this if you're using a graphing calculator. On a Casio, it is 2 to the right of alpha. And on a TI, I believe, I don't have a TI handy here, but I believe it's over to the right within those first 2 columns, maybe 2 or 3 down, okay? All right. So now we're going to try this guy. Couple of things to talk about here. First of all, 4 divided by 8 is not going to be written as 0.5, okay? We don't write that as a decimal. Our goal is to have our answer as one nice, pretty fraction. So instead of thinking 4 divided by 8 is 0.5, I want you to think of that as 4 over 8 and say, how can I reduce that? 4 over 8 reduces to 1 over 2, okay? Then I've got x to the 5 over x to the 4. When I'm dividing powers of the same base, I would subtract the exponent. So 5 minus 4 is 1. So it's x to the 1, but I don't need to say x to the 1. I'll just say x. And then I've got y to the 3 over y to the 7. Well, 3 minus 7 is negative 4. Then I would want you to think about another law that we had, 5 to the negative 4. That will equal 1 over, sorry, I said 5 to the negative 4 there, y to the negative 4. That will equal 1 over y to the 4, positive 4, okay? So a negative exponent tells us to flip the base, and then when I flip the base, the exponent becomes positive, okay? Now, if we're thinking about one big fraction here, that means I'm going to have a x on the top. I'm going to have a 2 on the bottom because it was 1/2, right? I don't need to put the 1 on the top because there's already an x there. I would only need to put that 1 on the top if there was nothing else on the top, okay? And then I've got that y to the 4 on the bottom. So that would be what my answer should look like, okay? All right, just gonna advance that. That's a little typo there. That should say y to the 4, just like I was talking about. Let's just take that away. Whoopsie, and put a 4 there. Okay. All right. Splendid. Okay. This, oh, let me clear that ink. Sorry, guys. Okay. This would have come right out of a 10C note. Just to review some vocabulary with you, okay? An expression of the form, we would say the nth root of x there, where n is a member of the reals, is called a radical. I'm just gonna hide my big old head for a second. The symbol, this guy here, is called the radical sign. N is called the root index, and x is called the radicand, okay? X is called the radicand. Okay, now, a mixed radical is any radical that is multiplied by a number other than 1. So an example might be 2 root 5, okay? That's like saying 2 times root 5. It's also like saying I have 2 root 5s. I have a root 5 here and I have a root 5 here and I put them together and I have 2 root 5s, okay? It means the same thing. An entire radical is any radical that is multiplied by 1. So essentially there's no number on that outside of the radical. Okay, so root 20. Now, if you go in your calculator and you type in 2 root 5 and you type in root 20, you'll get the exact same thing. Okay, now, a little word of wisdom to my new Casio users out there. If you type in root 20, it's actually going to give you 2 root 5, okay, because the new Casios will simplify radicals for you until they're in test mode. And just a reminder, when you write a test and when you write your diploma, you must be in test mode on those calculators, so that feature will get shut off, okay? So don't think you're at an advantage by having your calculator do that. You have to be able to show the work to prove that you know how to do it without your calculator, okay? All right. So the first thing we're going to do is go from mixed to entire. So essentially, I want everything underneath the square root, okay? Convert the following to entire radicals. Identify the values of the variable for which the radical expression is defined. Now, I'll talk more about that as we go. For this guy, there is no variables here, so we don't have to have that conversation. But what I do want you to understand is I want 4 to be underneath the square root. So I'm asking myself, the root of what is 4? Okay, and you know that to be the root of 16. So I'm going to change my 4 to be root 16. Now I've got root 16 times root 5. Once I have them both as roots, I can multiply the radicands together. And so that'll be root 80. Okay, so I changed my 4 to be root 16 so that I had 2 radicals being multiplied by each other. When I have 2 radicals being multiplied by each other, I just multiply the radicands together. Okay, so 16 times 5 is 80. That's where the root 80 comes from. Okay, 9 cubed root 2, same sort of game. The difference is it's a cube root now instead of a square root. Okay, so let me take you back here for a second. If I didn't know that the root of 16 was 4, how would I have figured that out? I actually would have taken 4 and squared it, right? 4 squared is 16. So then that's what tells me the root of 16 will give me 4. So when I come back to this conversation, if I'm looking for the cubed root of something to give me 9, well, the easiest way to figure that out is just to take 9 and cube it. Okay, so see how I wrote it here. I said, okay, I'm going to change 9 to be the cubed root of 9 cubed. Okay, I don't even care what 9 cubed is right now. I just know that the cubed root and the cube would have undone each other and left me with 9. So I know that the cubed root of 9 cubed is 9. Okay, Okay, 9 cubed times 2 gives me 1458. So I end up with the cube root of 1458. Now, little typo here as well. Sorry about that. That needs to be a cube. Now, I didn't do that purposefully, but that is a great conversation to have. That was me fighting with equation editor and forgetting that I needed to put a 3 there. But when you're writing these out, if you're talking about a cube root, every one you draw has to have that little 3 in there. If it doesn't have that little 3 in there, you're not talking the way you think you're talking, because it's actually looking like a square root, not a cube root. Okay, so make sure you communicate super, super clear. Okay, so a cubed root 3a. Now, the same conversation we just had is about to apply, right? I need to get that a cubed underneath a square root. So I'm going to think to myself, what is a cubed squared? And that would be a to the 6. Okay, but there's another conversation here. Anytime we have a variable, essentially when I write a variable, unless I'm told otherwise, that variable can be anything I want, right? That's the purpose of a variable, is it can be whatever, okay? When we have certain things in math, there are restrictions on what that variable actually can be. A actually can't be anything I want, because a can't be a negative number. If a was a negative number, take a look at here where I'm circling. If a was a negative number, I would end up with a negative radicand, and I can't take the square root of a negative number. Okay, so because of that, a can't be anything I want. And so what we have to say is we have to say, hey guys, a has to be greater than or equal to 0. A has to be 0 or a positive number, essentially. Okay, and so the way we write that is a has to be greater than or equal to 0, just like that. Okay, that's our mathematical way of saying, hey, a has to be positive. Okay, all right, so then back to the previous conversation I was having with you, I want to take this a cubed, and if I want it underneath a square root, I'm going to have to square it. Okay, so that's going to be the square root of a cubed squared. Now I have them both underneath a radical, so I can just multiply the radicands together. So a cubed squared is a to the 6, right? So I've got a to the 6 times 3a, so that'll be 3a to the 7. Okay. All right, 2b squared, cubed root of 4b to the 2. Now, do I need to talk about the fact that b has to be positive here? The answer is no. And the reason is, I've got a cube root. I can take the square root of a cubed number. The cubed root of negative 27, for instance, is negative 3, because negative 3 times negative 3 times negative 3 is negative 27. Okay, so for the values where the variable is defined, it can be actually anything here. So we say b is a member of the reals. Okay, now I need to get this guy underneath my cubed root, right? So to do that, I'm going to go the cubed root of that cubed, right? So 2b squared, all cubed. So 2 cubed is 8, and b squared cubed would give me b to the 6. Okay, so that's going to give me 8 times 4, which is 32, and b to the 6 times b to the 2 would give me b to the 8. So 32 b to the 8 altogether, the cubed root of 32 b to the 8. Don't drop those cubes or cube roots when you're doing your steps through here, okay? Okay, so we kind of just answered this question, but we can only take the square root of a positive number. Is this true for cube roots too? No, it's not. You can take the cube root of a negative number, okay? All right, now the next thing we want to talk about is simplifying radicals. When we simplify radicals, the goal is to make this radicand as small as we can, okay? And we do that by finding perfect square factors of the radicand And then we can bring them out because we know what the square root of perfect square factors are, okay? Now, what do I mean by perfect squares? Well, that's 2 times 2, 3 times 3, 4 times 4, and so on, okay? So what you want to do when you're solving these things is you want to make a list of your perfect square factors. So go ahead and do that. Give me your first 15. I'm going to ignore 1 because it doesn't do anything for dividing out. So I've got 4, I've got 9, 16, 25, 36, 49. Yeah, you're building all of that. Okay, it should look like this. Just as a quick aside, I know some of you may have been taught not necessarily to look for these perfect square factors, but to create a factor tree into prime factors and then group pairs together and pull that out. If that works for you, that's awesome. Okay, I personally find that takes a little bit longer and a little bit more work than what I'm doing here. But if you like that and it's working for you, don't change it. Okay, you can keep doing that. So I'm looking for a perfect square factor of 240. I know that I could divide by 4 for sure. I'm going to try 16. 240 divided by 16, that's 15. That's a larger number. I'm going to start with a larger number. If you wanted to start with a 4, totally fine. You just have to do this in 2 steps, okay? But I'm going to go right to the 16. So I'm going to break this down into root 16 times root 15. I know that 16 times 15 is 240. How do I know that? I just went in my calculator and went 240 divided by 16, okay? So I know that 16 times 15 is 240. But now I know that the root of 16 is 4. So I can simplify that to be 4 root 15, okay? Okay, then if we try the cubed root of 40, same process, different list. Now instead of looking for perfect squares, I'm looking for a perfect cube. So you want to think about 2 cubed being 8, 3 cubed being 27, 4 cubed being 64, 5 cubed being 125, and so on. I've got 6 cube, 7 cube, 8 cube. I go all the way to 10 cube in that little box. Okay, I can see that 40 is 8 times 5. So I'm going to break my cube root of 40 into the cube root of 8 times the cube root of 5. Okay. Again, don't forget those cubes for your root index. Okay. Then I know the cube root of 8 is 2. So I just change that to 2. And my final answer there would be 2 cube root 5. Okay. Okay, the square root of x to the 4. Well, there's 2 conversations I want to have here. First of all, I would want you to be comfortable to say the square root of x to the 4 is x squared, okay? And the reason I know that is because I'm trying to think what multiplied by itself gives me x squared. So essentially I would have x to the something times x to the something equals x to the 4. Right? You know that when you're multiplying powers of the same base, you add the exponents. So this would have to be a 2 plus 2 to give me that 4. Mathematically, you can take the exponent and cut it in half, okay, when you're taking the square root, as long as the exponent's even. Now, because we're talking about variables, we need to think about restrictions. When is this defined? Well, actually, x can be anything I want here. Okay, and the reason it can be anything I want is the first thing I'm going to do is take that to the power of 4. Any number to an even power is actually going to be positive. And so there's no way to actually get a negative square root here. So every value for x is allowable. So the way we handle that is we just say x is a member of the reals. Okay, and then when I take the square root of x to the 4, I get x squared. Okay. So most of this note is review from 10C. When we throw in the letters here, that's the new portion that you have to kind of just process today, okay? So part of today is about reviewing, and part of today is just wrapping your mind around the notion of dealing with letters and what is allowed and what's not allowed when it comes to having a letter underneath a square root, okay? X to the 10. Again, I'm looking at the square root of a variable to an even exponent. So x can be anything I want. There's no restrictions there. And then I'm thinking of something that multiplies by itself to get me x to the 10. That would be x to the 5. Okay. Okay, what about x to the 5? Well, this one changes things a bit because I don't have an even exponent. So it changes things in two ways. First of all, there's now restrictions. X has to be greater than or equal to 0. Otherwise, I would end up with a negative radicand, and I can't take the square root of a negative number. Okay. When we were working with 240 a couple of examples ago, the way I set that up is I created two roots, one with my perfect square and one with the leftover bits. Okay, I'm going to do the same thing here. The perfect square that I could take out would be the closest even number to 5, which would be x to the 4. So I'm going to separate this into x to the 4. Sorry, my animation was a little off there. I'm going to separate this into x to the 4 times x. And then I know, okay, that's cool, but the square root of x to the 4 is x squared. And so I just changed my square root of x to the 4 to x squared. So my final answer here would be x squared root x. Okay. So then, in a similar fashion, we're looking at the root of x to the 11. Again, this is an odd exponent. So I do have to state that x has to be greater than or equal to 0. And then I'm going to split it into my perfect square piece and my non-perfect square piece, or my leftover piece. Okay, x to the 10, I would be able to take out as a perfect square. So I'm going to separate this into the root of x to the 10 times the root of x. And then I know that the root of x to the 10 is x to the 5. Okay, so my final answer here would be x to the 5 root x. X to the 5 root x. Okay, all right, so now we're just going to end with maybe just a bit more complicated, but not really. All we're doing is we're sticking the numbers and the letters together. So you just deal with the numbers and you deal with the letters. And I think, you know, you can say you disagree with me. I think the easiest way to do this is to do it like I've been setting you up, where you take out your perfect square, and then you have the leftover bits, and then you figure out what the square root of that perfect square is. Okay, so when I look at 12 x to the 10 y to the 4, well, first of all, I need to think about when x and y are defined. These are both even exponents with a square root, so there are no restrictions. Both x is a member of the reals and y is a member of the reals. Okay, now when I'm looking at just 12, I can take out a 4, that's my perfect square factor, and I'll have left over a 3. X to the 10, I can put all of that in my perfect square section, and y to the 4, I can put all of that in my perfect square section. Okay, so I have the root of 4x to the 10, y to the 4. Those are all the perfect squares that I can deal with. And then my leftover bit will be root 3. Okay, now I actually take the square root. So the square root of 4 is 2. The square root of x to the 10 is x to the 5. You're just dividing that exponent, right? And the square root of the square root of y to the 4 is y to the 2. Okay, so I end up with 2x to the 5, y to the 2, root 3. Okay. All right, good job, guys. Root of 63, n to the 7, p to the 4. Now, n has a odd exponent, so n has to be greater than or equal to 0. P has an even exponent, so p can be a member of the reals. Now, I'm going to separate it into my perfect square and my leftover bits. For 63, I can take out a 9, and my leftover bit will be a 7. 9 times 7 is 63. For n to the 7, I could take out n to the 6, and my leftover bit would be an n. And for p to the 4, I can take all of that out, so that will go into the perfect square section. So I've got the root of 9 n to the 6 p to the 4 times the root of 7n. Now, I know the root of 9 is 3, the root of n to the 6 is n to the 3, and the root of p to the 4 is p squared. So I end up with 3 n to the 3 p squared root of 7n. Okay, so you take out, or you break it into your perfect square portion and your non-perfect square portion, and then you take the square root of your perfect square. Okay, same conversation, it's just we're dealing with cube roots now. As soon as we're dealing with cube roots, the x and y, it doesn't matter whether they're even exponents or odd exponents. I can take the cube root of a positive and of a negative, so they are both members of the real. Okay. Okay, same thing. I'm going to separate it into my perfect cubes and my leftover bits. For 16, that means an 8 in my perfect cube and a 2 in my leftover bit. For x to the 4, every x cubed is a perfect cube, right? So I can stick an x cubed in my perfect cube section, and then I'll have x as my leftover bit. For y to the 10, well, I could do y to the cube, or y cubed would give me y to the 9, right? So I can actually take out y to the 9 here. Every set of 3 would be a perfect cube, okay? So y to the 9 is going to go into my perfect cube section, and then the leftover bit, I'll have a y on the other side there. Okay, so I've got the cubed root of 8x cubed y to the 9, and then my leftover bit would be the cubed root of 2xy. Now, the cubed root of 8 is 2, the cubed root of x cubed is x, and the cubed root of y to the 9 would be y to the 3. So final answer here, 2xy to the 3 times the cubed root of 2xy. Okay? Awesome. What about the 4th root of x to the 7 then? Well, I got to talk about restrictions first. I have an even root index. So even root indexes or indices behave the same way as a square root would. Because I have an odd exponent, then I have to say that x has to be greater than or equal to 0. Okay. I can't put a negative number in here because a negative number to the exponent of 7 would give me a negative number, and the 4th root of a negative number is not possible. Okay. All right, then I think, okay, well, let's separate this into my perfect 4th and my leftover bit. My perfect 4th would be x to the 4, and then my leftover bit would be x to the 3. Okay, remember, this line still equals this line because x to the 4 times x to the 3 is still giving me x to the 7. Okay, but I know the 4th root of x to the 4 to be x. So my final answer will be x, 4th root of x to the 3. Okay. All right, my friends, that is it for our introductory lesson. Here is your homework. And give yourself some time, give yourself some processing time. I really want you to think through this whole concept of what values are allowed for my variable, because that's kind of the newish piece for today. And then just get comfortable simplifying radicals again from 10C, okay? You guys can do this, I know you can. Please connect with me if you have any questions, and I'll see you for our next lesson when we begin adding and subtracting radicals. Be very fun. Take care, guys.